Welcome back to Numerical Methods. Today we're going to continue our discussion on boundary value problems and wrap them up. So just as a reminder, last time we started talking about ODEs, and we realized that we first needed to, we first talked about the one method of doing that where we reduced our set of ODEs to a series of first ODEs. And then we could use that in, say, the shooting method, where we would guess initial conditions and predict the values at other boundaries. We could then use a root finding method, say, to find out what the correct guess or the correct other initial condition is. Or if it was linear, we could use interpolation to find that from only 2 shots. Then we talked about finite difference methods, where we were going to generate nodes or a mesh along the length spanned by the boundary conditions. Then we could turn those differential equations into a series of equations for each point along the mesh. And then last time, we talked about how we can solve those mesh points using linear equation methods. Today, we're going to wrap up by talking about nonlinear solutions to those methods, where we're going to have to use an iterative technique to find the points along those lines. Additionally, just as a reminder, we said that we could do this for Dirichlet boundary conditions. Remember, that's a case where we could say something like y at 0 equals 5. And we also talked about Neumann boundary conditions, where we would say maybe dy dx at x equals 0 is equal to 5, right? So Dirichlet is a value and Neumann is a derivative, right? And so we're going to address both of those again today in terms of nonlinear finite difference methods. So how we're going to do this is using a series of points along these nodes, so nodes along these areas. One way could be to use a root location method for these equations, but the much more common one that we're going to take is using successive substitution ideas in order to solve these problems. So the general route that we're going to take is we're going to generate nodes or a mesh in 2 dimensions along those points. So if I say I know information at, if I want to look at x equals 0 to x equals L, I'm going to generate nodes along that, that line. And then I'm going to solve out these, and then I'm going to find an equation for each point or each node along said line, and then come back and look at, then use a nonlinear solution method such as Gauss-Seidel or Newton-Raphson to solve out those problems. Right? And so we end up having this iterative solution. So the best way, once again, to sort of see how this is done is to see an example. We're going to go back to our example of a rod connecting 2 different temperatured plates. That rod is going to have length L, and there's going to be both heat conduction along this line, heat convection off of here, and then radiation. In total, this can be described by this equation, which says 0 is d squared t dx squared plus h prime t infinity minus t plus sigma prime times t infinity to the 4th minus t to the 4th. And then we can look at this for a certain length, say 10 meters, a spacing of 2 meters, and these different boundary conditions. So the first thing that we need to do is we need to convert these equations into a usable form. So here's our general equation, and here's this rod with all these nodes in. So let's first make a generic equation and see how we're going to do that. What we're going to do, just like we sort of did before, is we're going to remember that d squared t dx squared is my differential equation. And we can use a finite difference formula to find out what that equals, right? So using a central finite difference formula, I can say that d squared t dx squared is t I minus 1. So the previous point minus my current point plus my next point. So ti plus 1. Let's call this at ti. Right? So this is my differences, and then I put this over dx squared. Right? So this is my conversion using central difference formula for finding a second derivative. So I can substitute this in to this top equation, and I can say dti minus 1 minus 2ti plus ti plus 1 all over delta x squared is now everything on the right-hand side of that equation. So I could say minus h prime t infinity minus t plus sigma to t infinity to the fourth minus t to the fourth. Okay, so now what we want to do to get a series of equations is to isolate that ti. We want to look at it for each individual node. So I need to get ti all by itself. What I'm going to do is I'm going to multiply both sides of this equation by delta x squared, and then I'm going to pull this ti term. I'm going to pull these ti terms that are sitting on the right-hand side of the equation over to the left-hand side equation. So when I do that, I get negative ti minus 1 plus 2 plus h prime delta x squared times ti minus ti plus 1, and that's all equal to delta x squared times h prime t infinity plus sigma prime t x t infinity to the fourth minus ti to the fourth. You'll see what's, give me a second and I'm going to clean this up. So I'm going to just shift everything around to isolate ti. So when I do that, I get ti is equal to this delta x squared h t infinity plus sigma prime times t infinity to the fourth minus ti to the fourth. I close that parentheses plus ti minus 1 plus ti plus 1 all over 2 plus h prime delta x squared. Okay, so we've got our functional form. We have a ti that's isolated on the left-hand side. On the right-hand side, we have a bunch of constants, but we also have a few ti's and ti's plus 1 and ti's minus 1. This is going to be okay, right? Because we're going to use some iterative methods. Notice, though, that we have this ti to the fourth. I couldn't get rid of that, so I have this system which is nonlinear, right? I don't just have ti's. Okay, so we have the baseline set up. We now need to determine what our boundary conditions were. From the set of the problems, we had found out that T0 equals 300K and T5, so at that fifth node over here, we had 400K. This is just given. So now we need to set up our system of equations. We need to determine how many nodes we're going to need and then write an equation for each individual node. So if I have if I'm moving in increments of 2x, if I want delta x to be 2, I know I'm at 0, so that's 2 feet, 2, 4, 6, 8, 10. So that gives me 1, 2, 3, 4 nodes that I need to work with. I need 4 equations. So let's write the first, our T1. So I'll put this here, so T1. So I can go in, T1 is delta x squared times h prime t infinity plus sigma prime times t infinity squared plus T1 to the 4th plus T0 plus T2 over 2 plus h prime delta x squared. And I can go ahead and do this again for T2. This stays the same. I now have temperature 2 here. I have the temperature 2 here, and then 1 and 3. Okay, I'm not going to go ahead and do out the equations for the next 2 because it's a little repetitive. It just switches out, and you have 3, 2, and 4, and then you would have T4. You'd have T4 here, you would have T3 here, and you would have T5 here. Okay, so we can set up all these equations. Now we just need to solve out this system of equations. So here, let's take T1 as our starting point. So I've pulled this equation forward. This is just our generic T equation. I've written it also up here to sort of serve as a reference. All I need to do now is to go in and solve this T4, this T1 out. So let's go back. So if I look at this, you'll notice that I need T1, T0, and T2. Well, I have the value already for T0, right? That's given. That's this 300. I don't have a T1 value, right? This is why I'm solving the problem. And I also don't have a T2 value, also why I'm solving the problem. Therefore, we have to make a guess. If you remember all the way back to sort of our root finding and our simultaneous equation solving, we have to have, for nonlinear systems, we have to have an initial guess. In this case, let's just guess t equals 0 and see what happens. So now we can go forward. I've substituted those equations, or those numbers in here. So now you'll see I have T1. I'm just going to guess 0. T0, that's a given, that's 300. And I'm just going to guess 0 for T2 as well. I can then go in and solve this out. So let's do this together. So I have T1 is 2 squared. That's just my given. I then have 0.05 times 200 plus 2.7 times 10 to the negative 9th times my t infinity, which was 200 to the 4th, minus 0 to the 4th, plus 300 plus 0. I can put this all over 2 plus 0.05 squared. 0.05 times 2 squared. And then I can solve this all out. And when I do solve this all out, it ends up being 162.4. So now I have my new guess for T1. I previously had a guess of 0. Now I have my new guess. Now I'm ready to go ahead and do this out for T2. So remember, it's quite efficient if we're using Gauss-Seidel, not the Jacobian method. So when I go in to solve this T2, I still have to have my initial guess for what that T2 is, but I'm going to use the T1 calculated above to plug that in here. So I can go ahead and do this out. I've got T2, which which is going to have sort of that same general form. So that's 2 squared times 0.05 times 200 plus 2 times 10 to the negative 19th times 200 to the 4th minus 0 to the 4th, right? Because I'm still guessing 0. Plus, now I'm going to substitute in my T1 guess, which is, or my new T1, which is 162.4, plus T3, which we don't know that. We're just going to guess 0. We put that all over 2 plus 0.05 times 2 squared. I'm going to do this all out, and this gives me 99.85. Okay, so we can go in, we can calculate these at these two different nodes. Oops. So I've just pulled those values forward and shown them here. We can now do this for T3. I'm going to go a little bit faster. T3 is just going to be equal to, I'm going to have a 0 in here, have that 99.85 in here, and then for T4, I'm going to use 0. I'm not going to go out and punch out all this, write out all this math again, but this is equal to 71.4. Oops, there we go. We already have this written out. 99.85 and 0. Okay, so now I can go ahead and do this for number 5, or point number 4. So once again, we're going to have a place where we need to guess what T4 is. Remember, that's going to be 0. We're going to have a T3, and this is coming from that value that we just calculated, and then we have T5. Remember, T5 was a given, right? That's that endpoint. That's what's coming at the at that last point. That's going to be just 400K. All right. So I can go ahead. I can punch all of this in, and I'll find that we have 240. Okay. So now we've gone one sort of loop from the left to the right, solving out our different TNs. But let me make a quick point. We have this issue where when I calculated T1, I had guessed that T2 was 0. In fact, we now see that T2, or our next guess for T2, is 99. Definitely not 0. Additionally, we also had this 0 in here because we were guessing that T1 itself was 0. And we now have calculated a number that T1 is 162. Definitely not 0. So that number we know is going to be off. So we need to go ahead and do this again. So we have to iterate these nodes. Here on the left-hand, on the right-hand side of the screen, I've put our first round of iterations guesses for what my different T's are. So I'm going to go ahead and need to do this again. So here's up at the top, here's my equation that I'm going to use, and I'm going to substitute in my appropriate values. Here, which is my T1, I put in 162.4. That's because I'm coming from that first guess for T1. In the case of that T1 point, right, my Ti minus 1 is T0, which is 300. So I keep the 300 from there. I would also then, in this last term, need Ti plus 1, or T2. There we're going to go ahead and use that 99. We're going to use that 99.85. When I do this all out, I end up getting a total value of 204. I can do the same thing now for T2. Here in the T2 spot, I'm using 99.85. For my T1 spot, I now use the 200 that used to go in, that I found from T1. I'm then going to pull the 71.4 in for T3. Okay, I'm going to calculate this all out, and I end up with 150. I can now do T3, where I use the 71.4. My old guess for T3 goes into the T3 spot. My guess for my newly calculated T2 comes in here, and then I'm pulling my previously calculated T4, which was 240.3. This is going to give me an updated guess of 203. And then finally, I'm going to do this for T4. Here, I use my previous estimate for T4, 240, my newly calculated T3, which is 203, and then I'm going to bring in that T5 for my other boundary condition, which is 400. I then can go ahead and calculate that that value is 284.1. I then need to repeat this because clearly 284 is not the same as 240. And I can repeat this again and again and again. I'm not going to do this out because this gets quite repetitive, but if I repeat this roughly 10 times, I find that my values stop changing. Once again, we could use different metrics for determining when those values stop changing, right? Approximate error being a good one, or we can fix the total number of times we do the iteration. And remember, we have to pick the worst value. So whichever is giving the largest error, that's the error we have to use for determining our accuracy. So I can do this and I can punch this all out. And when I do this and I do the iterations, I get these values. So I can then go ahead and plot these values as these points along the nodes. So here, 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 and here. Now, before we go on, I do want to comment that the choice that we make for delta x matters, right? Just like we had talked about previously when we're talking about central difference formulas for differentiation, right? My my dt dx has an error on the order of h for this second derivative. So if I want to improve the estimate of my error, I have to decrease that h size. So I'm sort of stuck with the error or the error of that h. So if I want to get a better solution, I need to go ahead and take a smaller step size. Actually, I want to correct myself. Sorry, this is order h squared. So I do need to come in and start bringing that error. So to check to see if I have a good approximation to the solution, I should go in, divide everything in half, and make sure that I have a solution that converges. So not just converges along this route, but then if I say go from one step to the next step, it doesn't change, right? I get the same answer from one step to the next. Now let's look at a similar example, but instead of using Dirichlet boundary conditions, let's look at an example where we have Neumann boundary conditions. We're still going to keep the fact that we have a temperature of 400 on this side, but on this A side, we're going to say that dt dx is 0, right? There's going to be no temperature change across that boundary. So we're going to go through the same series of steps to look at this. So the key thing, if you remember back from last time, is we're going to need to know what the temperature is at this node 0, so T at 0. And in order to implement this boundary condition, we're going to need to use an imaginary node. Because remember, our solution or our numeric answer to this d squared t dx squared needs to look both right and left. We need to come up with this imaginary node. So we're going to go through the same steps as follows. First, we're going to need to convert our equations to usable forms. This is going to look identical to what we had previously for the Deer Lake boundary conditions. So I'm not going to go through that again. The key part being, of course, in summary, that we used a central finite difference approximation to replace this d squared t dx squared, and then we could rearrange it to isolate one ti, and then we would have some ti terms over on the other sides of the equation. Now we need to determine our boundary conditions in the form of an equation. Well, we have sort of two things. We have our dt dx at 0 equals 0. So that's on this side. And then we have t at 5, at that node 5, is going to be 400k. We're still going to assume, right, that we need to have four nodes. Now we need to set up our system of equations. The first one that we need to do is look at node 0. But and remember, though, that node 0 is going to require us to know information about the node to its left. So we really need to look at this node -1. So here we have it sort of drawn in. So we need to figure out what that temperature is at node -1 in order to understand this. So we can use our dt dx, remembering, of course, that we can use a finite difference, a central finite difference formula again, in order to find out what that temperature is. So rearranging my central finite difference formula for dt dx, we find that t-1 is equal to t1 minus 2 dx times dt dx. In this case, we have t1 minus 2 times 0 equals t1. So we now have that initial guess for what t1 is. Now I can go ahead and write out my different equations for the different nodes. So for t0, t1, t2, t3, and t4, they're going to look pretty much just like the ones on the previous slide, the previous example. But of course, we have to write out the equation for t0 and t-1. We don't get to have those as a gimme. So once we've set up these systems of equations, I can go in and start solving them. So the first thing that I need to do is I say ti-1 equals ti. If we're assuming as a start that all of my nodes are 0 Kelvin, I find out that ti-1 is 0. Then I can go ahead and start addressing my my actual nodes, so not my imaginary nodes. We find out that t0 is delta x squared times t infinity plus sigma prime t infinity to the 4th minus 0, right? So this is t0. We guess that they all were 0 plus ti-1 and t1. If I plug this all in, I find that my new guess for t0 is 26.0. I can go through and start doing this for each individual node. For t1, I have my guess of 0 for t1. I have my guess for t0, and then my guess for t2, which is 0. So I can plug all this in. I have 37.9. I can do this for t2, using, of course, 0 for my guess for t2, using 37.9 as my guess for t1, and using 0 as my guess for t3. If I plug all those numbers in, I get 43.2, and then I'm ready to go on to T3 using 0 for my guess for T3, 43.3 for T2, and 0 for T4. If I plug all that in, I get 45.7. And then I can go ahead and do this for T4. I have my initial guess of 0 for T4, 45.7 for T3, and then 400 for T5. This is our boundary condition, T5 equals 400. Okay, if I do this all out, I get 228.6. So now all I need to do is repeat this again and again, just like I did for the Deer Lake boundary conditions. If I do this and I repeat it enough times, I find that I get this solution. And you can see almost immediately that I'm going to probably need to do this quite a few times because I'm ending up having my initial guess at T0 is 26 Kelvin, but after I get convergence, I'm an order of magnitude larger, 208.3. But then we can still use those same sets of ideas. Okay, so I can plot this out. We can see immediately that my derivative, or my line down here is flat as I go from 0 to 1. This is because, as it should be, I should have a 0 slope here, and then it's sort of that temperature takes off. Before we go any farther, I would like to make a few comments. So when we have these nonlinear solutions, and particularly when we have these nonlinear solutions to second order equations, we end up having sort of two forms. We end up having this average, right? I am taking the point on either side of my information from the point on either side of the node that I'm looking at, and then we have some sort of correction, which is all the other stuff that's happening, all the other physics that's happening in my system. This means that my initial guess matters, right? Because I'm averaging the points to the right and the left. So what I'm guessing on either side of the point that I'm sitting at is going to matter. So one way to improve my guess is to possibly interpolate. If I know what points are on one end, what points are on the other end, instead of putting zeros everywhere along that rod, maybe I can put, I could interpolate. Let me try this differently. Instead of putting zeros all the way between the rod, so that would maybe show up as like this 0 line, I could interpolate along that line just as an initial guess. This may help my solution. The other thing that occurs is that order matters. If I go from left to right or from right to left, I'm going to have different behavior. In this case, if I have a low number and then a bunch of zeros and I sort of move this way, my rate of change is going to be slow, right? Because I have a bunch of these zeros. A bunch of these terms are just 0. If, however, I had started at the hot end with 400 and I went backwards, now this one term would have been 400 compared to 0 and 0. I would have had a bigger number in there, and I would have most likely converged much faster. So we have to be careful when I'm doing these systems of equations out, because the guess matters, and the order in which I do the successive substitution also matters. Okay, so this is the end of the major ideas of boundary value problems. Next, we're going to switch and we're going to go look at how MATLAB is going to solve those boundary condition problems. MATLAB has a built-in solver called BVP4C that will solve our boundary value problems. It's going to have this functional form. It's going to have an ODE function. It's going to have a boundary condition function, and then it's going to have our initial conditions. These different functions are going to be a little bit sort of odd. So let me walk you through how this is going to work, and then I'm going to show you in MATLAB. So first, ODE fun is just our functions. That's going to behave just like we had for our normal ODE solvers for initial value problems. So think of that's just a function that's going to return how those functions change. It has to, though, be a series of first order ODEs. My boundary condition function is essentially going to is set up such that I get zeros in here. It's a function that returns zeros when y equals the correct boundary values at the boundary condition, at the boundary values. And then the last piece, this solint file, is sort of an odd structure. It's going to have, on one hand, a vector, a column vector that contains all the nodes that we're looking at. So if we wanted to go from 0 to 10, we would have 0 in that first field, 10 in the last field, and then maybe 2, 4, 6, and 8. Right? So these are essentially this first part of solint is going to be my x is where the nodes are, and then it provides the set of those boundary values. So say, I don't know, 1 and -1, and that 1 would correspond to 0, and that -1 would correspond to 10. It's going to be a little bit funky, but bear with me, and we'll walk through each of these. So let's tackle that first piece first. So let's use MATLAB to solve this equation, dx d squared y dx squared plus y equals 1, subject to the boundary conditions y of 0 equals 1 and y of pi over 2 equals 0. So the first thing that we need to do is break this up as a solution or as a series of ODEs. So remember, we can say dy dx equals z, and then we can substitute this z term up here to find that dz dx equals 1 minus y. All right, I'm going to see you over in MATLAB where we're going to implement all these different functions that we need to get our solution going. So here we are in MATLAB. So now we need to go in and we need to set up our different functions. Let's first set up that ODE function that we just talked about. So we can do this just like we had before. We say function, some sort of dy is equal to ODES times of x and y. And then as good programmers, we can always put in that end right away. So now we just need to plug in our two equations as a single number. So remember, we first have z, which is going to be y2, and then our dx, dz dx is 1 minus y of y. Okay, I go in there. I'm good to go. I can just save this function, and I've got my first piece of the puzzle solved. Now I need to put in those boundary conditions. So we need a function that's going to hold our boundary conditions and equals 0. Maybe I'll put this down here. Remember, we need y of 0 to be equal to 1 and y of pi over 2 to be equal to 0. We need to formulate these in such a way that at the beginning of the solution, this formula is going to return a 0 and at the end of those x's, it's going to also return a 0. So we're going to put these in here. So we can say function, these residuals, so maybe R is BCS, so for boundary conditions. It's going to take in the y, the farthest to the left, so call it YA, and then the y farthest to the right, we'll call that YB. And then we can just put that end in. Now we need to give a functional form that will be equal to 0 when YA is equal to 1. Well, this is going to be when YA of 0 is equal to 1. So if I put YA 0 minus 1, that's going to then tell me, that's then going to return back 0 when YA 0 is 1. Exactly what we want. So then we can put in, we need when YB is 0, we put YB 1 equals 0 because when it's 0, Y is 0, we're good to go. We can close that setup. Oops, I'm sorry, not equal 0, we just leave it as YB. That's because when YB is 0, that's going to be a 0. Okay, so we have this function now set up. So I can save this as well as BCs, and I'm ready to go on to my next function. I want to make a quick correction to what I said earlier. Before my boundary condition problems, I had a 0 here. It should be a 1. Sorry about that confusion. So this should be a 1. This function is going to be, this is going to be a script. We've done the function setups that we need. Now we just need to do a few housekeeping things to set everything up. So let's first clear everything from my memory, and then I'm ready to set up that solint piece. So we're going to do this. So we're going to say sol init is going to be my bvpinit, which is a built-in MATLAB function that's going to create the structure. And we're going to then give it the series of x's that we want, right? You can see it pop up. It's going to tell us that it wants that series of x's. So we can use line space to create that series of x's. If we want to go from 0 to pi over 2, and we could say maybe in 10 spots. So we can put in a 10 there, right? I want to go from 0 to pi over 2 in with 10 nodes. That's that first piece. Now I need to give it my those initial conditions setups. So here we go. We can give it 1 and 0. And then I can close that out. I'm sorry, 1 and -1. There we go. I can close that out. Now I'm ready to go in and use my BVP4C. So I'm just going to say I'm going to store that solution in, I'm going to store this functional form in this word called sol. Okay, so this is going to be BVP4C at my function call. So that's the ODES, right, which I've put in there. Then I'm going to call my boundary condition, so at BCS. And then I'm going to call that sol init structure, which I built above. Okay, so now I have sort of everything built up. I can now go ahead and make my series of x's again. This is because this is the way MATLAB likes stuff, so I have to put in my x's, my series of x's again. Just can copy paste those. I'm ready to go in and get my y, and here I'm going to use the built-in MATLAB function that's going to evaluate BVP for C. So this I do as deval sol x. And then I'm going to just have this plot x and y for us. Okay, I'm going to save this and then we'll run it. And then I have my, now I've saved my set, I've made that one fix, and then I have my initial guess for my y, and then I have my my initial guess for dy dx, so that's that -1. These are just sort of initial guesses for the problem. The boundary condition formula is going to actually enforce our boundary conditions. So now that I have everything lined up and saved, I'm ready to run it. You'll see that it'll run through, it'll pop up, and we have our final solution. We can see that we have our one at the we see that we have 1 at the top, and it's coming down to our other boundary condition of 0 at the at pi/2. This is exactly what we told the solution to do. And then we also can see what our dy dz dx would be. Okay, so in summary, let me go back. In summary, we have to set up a few functions when we're using BVP for C. We need to set up our ODEs. We have to set up our boundary conditions such that it returns a 0 when the boundary conditions are satisfied. And we have to set up this solution's initial conditions. That's going to have the series of x's over which I'm looking and the initial guesses for my ODE, my first order ODEs. Then I set up this solution call, which is going to wrap everything together. It's got my ODEs, my boundary conditions, and my initial conditions. I then solve over the space that I'm looking for, and I use deval to solve my boundary conditions. So what you'll notice is this is a lot more work and a lot more functions going on that we need to do to solve initial value problems in MATLAB. This is because boundary condition problems are just much harder much harder to solve. Okay, hopefully now you get a good idea of how to use the inbuilt MATLAB functions for solving boundary conditions. And I'll see you back over in PowerPoint. So that's going to conclude our discussion on boundary conditions. So we took a few different tacks. So one tack was in the shooting method, where we would reduce our ODEs into a series of first order ODEs. Then we can make predictions on, or we can make guesses as to what all the initial values were at one boundary, project out to the other boundary, and see if we ended up with the right guess. Then we could either iteratively or through smart methods to determine what value I should use as my second guess for my ODEs. We then talked about saying that if we had a nonlinear solution, we needed to use a root finding method. We then moved away from the shooting type methods where we're predicting out to finite different methods. In this case, we generate nodes along the space spanned by my boundary conditions. So I break up my problem, instead of by a series of ODEs, I set it up as a series of those finite differences at points along my path of interest. I then turn my differential equations into a series of equations by using, say, the central difference formula. If I have a linear, if those equations are linear, I can use linear algebra to solve those methods. And if not, we have to go and use nonlinear solution methods such as Gauss-Seidel to solve our problems. We then talked about how we can implement some of these in MATLAB. I hope you now have a firmer understanding of boundary value problems, and I'll see you in class.